So thank you. So hopefully this will be a reasonably quick talk. The work today has contributions from 4 previous or current master's students, all of whom have written their theses on aspects of this problem, largely because this is what NSERC gave me money to study for the last 5 years. So assessing the statistical performance of time series interpolators. So a time series, we've been using this language. You all know, I hope, what a time series is: a sequence of numerical measurements, typically numerical, ordered sequentially with respect to an index variable, which in the case of most of our examples in environmetrics is time. Here's a time series. In the wild, this comes from the fields of our profession: astrophysics, helioseismology, economics, meteorology, oceanography, water tables, you name it. When we measure something and we do so across time, we get a time series. These, and this is where I entered into this research area, often have embedded periodic structure, which is what I did my PhD on, and that's what I'm primarily interested in. Our common analysis objectives are to forecast or to compute statistics. That's largely what we do on our time series. If we take a Fourier transform, a wonderful mathematical tool, we obtain a frequency domain representation of a time series, and in that domain, we still do statistics, but our statistics are computed with respect to frequency instead of time. And this is traditionally done through the medium of estimating the power spectrum of that data. The common practical challenge, which has been mentioned by many people so far, is that data is not perfect. It does not descend from up on high, written upon a tablet with every observation carefully recorded in all of its beautiful precision. There are lots of things that can go wrong. Our instruments can fail. Our experiments can fail. Our recorders can just not record the data properly. You could have a power outage. You could design your structure and your experiment so that you don't record on the weekends, like the business cycle. These missingness patterns may have uniform or non-uniform probability structures. There's an entire literature and field of people who specifically study that. We're not going to belabor that point. So by definition, what I'm going to call interpolation is the estimation of the values of the missing observations of a discrete set of known time points where we simply don't have observations at those time points. These are some of the methods that exist in the classic literature. You've probably all heard of a Kalman filter. We also have methods of spline fitting. We can do moving averages. You'll notice, though, that none of these methods have anything to do with the fundamental statistics of a time series, which is to say, the autocovariance structure. There is one method that does exist that does use the autocovariance structure explicitly, and it's an old one, and I'll mention it in a minute. Typically, in a classical time series analysis, we would like the time series to be stationary because that makes a lot of the problems we want to try and solve tractable. It's the drunk in the lamppost argument from statistics, folks. Why do we want stationary? Well, because when it's stationary, it works. It isn't because the real world is stationary. It's just that all of our theory for a lot of the classic methods only holds in this little bubble of the world. We'd like a constant mean. We'd like constant time invariant variance. So as soon as you throw a non-constant mean or a non-constant variance, you kind of blow up a lot of the classical theory. Now the mean, we can deal with that, and trend analysis is an old and very well-established field. Non-constant variance can really mess up your day, and that tends to be the first entry into the world of non-stationarity. Now, as an aside, the problem with stationarity and non-stationarity is that stationarity is very easy to define. And non-stationarity is everything else. And you can't even really define it because there's so many ways you can break your tiny little working bubble. So I'm going to break it in a very particular way today. We also usually, for all the classic estimators, the ones that are robust, that have well understood properties, whose asymptotic behavior was worked out in the 1920s and 30s and 40s, require contiguity of measurement. If you have missing observations, your estimators no longer work with all of their guaranteed properties. So this is where I entered this problem. As I started grad school, and I went, yeah, but real data doesn't act like that. And my PhD advisor said, yeah, it doesn't. So what are you going to do about it? What do we do about it? And that started me down this road. So how can we try and repair a non-contiguous, non-stationary time series, rendering it then suitable for use using classical algorithms? Well, there are many ways of doing so. I'd like to tell you about one of them and about something we've developed to help us do more of them. Contribution number one, this is my PhD. So what year is it? 11 years ago today, I was wrapping up my PhD and I developed what I named, I had to give it a name. It couldn't just be the interpolator I made. So I called it a hybrid Wiener interpolator because it takes Norbert Wiener's classic 1949 autocovariance forecasting method that uses the autocovariance structure and embedded it in a larger EM framework that allowed for use of some classes of non-stationary data. And we used kind of the Cleveland style of thinking about time series, of having sort of a piece that is a trend with certain amounts of properties, a piece that is periodic deterministic structure, and a piece that qualifies under Wiener's theory, something that is stationary. So that's a non-stationary series by definition, because I've thrown in a trend and I've thrown in periodic structure, and it doesn't meet any of the classic definitions. This was chosen very specifically because this turns out to be good enough to model a wealth of real-world scientific time series. Now, there are exceptions, many exceptions, but for the kind of data I was dealing with my PhD and that I deal with most of the time in my research, this actually models that data pretty well. So that was developed a long time ago. I'm not going to talk about it much today. Contribution two, and what I've been working on with my students is, okay, how do you assess the performance? Great, you've developed an interpolator. It's the best idea you've ever had. It works super well. How do you know it works well? How do you figure out whether it's doing a reasonable job of interpolating your series with your missingness? So we developed a framework, and this started with a master's student who graduated 3 years ago named Sophie, and she developed an R package as the primary contribution of her master's called Interp Tools. And it's on GitHub, and you can grab it and play with it if you want. It has 5 different primary veins of work. Number one, it lets you make artificial data. This is nice because then you know what the real values are, and then you can test against ground truth. Again, it uses the Cleveland structure the same way that the hybrid Wiener was set up for, but little caveat, you can pass in whatever you want. It supports you just giving it a time series. You're like, here is a time series. It is complete, it is contiguous. Let's test interpolators on this complete time series. Number two, it allows you to impose gap structures. And you can do this using 2 different parameters. One is what proportion of the time series would you like to have go poof and disappear? And how wide would you like the chunks of missingness to be at maximum? And we call these P and G. And so you can see up the top, just like a randomly generated time series and 2 different versions with different P's and G's with missingness imposed upon them. Number 3. It has a very nicely done, parallel, reasonably fast algorithm for running any of these that you like on this synthetically generated gappy time series. These are every algorithm we could find in the literature when Sophie was writing her master's, including, down at number 18, mine. It also lets you pass in a function that can do interpolation to a time series and therefore test a custom designed user algorithm against these 18 standard methods. As many as you want, depending on how much computer power you want to throw at it. Sophie's master's took about 3.5 months to run on a reasonably powerful 32-core computer, and that was her simulations for her master's. And then we quantify how well they do. So how well does the interpolated series capture the essence of the original series? How much difference is there between the points? So then, we're statisticians. What metric would you like to use? So what's your favorite way of measuring divergences from original series? Here you go. These are all supported. And if you can come up with anything else, you're welcome to integrate it into the package as well. These are, again, every method we can come up with as of 2020 that someone had ever used for comparing one time series to another time series. So you don't need absolute percent error or wise root mean square deviation. They're all in there. You can just give it a list of which ones you want to use, and it will measure all of those for all of those interpolations. Number 5, well, before I quite get to that, this is how it stores it. Unfortunately, it's R, so how are you going to store all this data? So it's a list of lists with a bunch of functions that can extract what you want and how you want it. So it's actually pretty user-friendly. But what we end up with is, here's your original time series. That can either be provided or you can synthetically generate one under certain criteria. Here is the set of all of the parameters of all of the missingness you are interested in, all the P's and G's you'd like it to randomize across. A choice of K, which is basically how many replicates would you like to do for every choice of P and G, every one different. Which methods would you like to do? And which metrics would you like to apply? And as you can see, that exponentially starts to snowball. You start doing more and more methods and more K. Computer power starts to become a problem. But the nice thing is you can always split it off and just do one set of it and then do another set later, and they are comparable. Then across the set of synthetic replicates, we have visualization tools. We can visualize the distribution of those divergences. We can get density functions. We can extract pieces from the density functions. Look at the medians or the quartiles or whatever you would like to look at, whatever you choose to be the most important factor of that distribution of divergences. We support generation of all these lovely surfaces across P and G. It integrates Plotly graphics, so you can actually rotate your lovely interacting surfaces and try and actually get the right angle to take a snapshot to make it for your paper or whatever you want to use it for. You can do this across different methods or across different variants, whatever you'd like to do. Palettes are supported. You can extract slices. So once you've generated this sort of discrete field of performance across the proportion missing and the gap length, you can also fix one of those two values and extract quantiled series that tell you sort of performance as gap width increases, say. You can pull out heat maps, which are actually just a lot nicer to look at a lot of the time. The surfaces look really pretty, but when you try and actually stare at them and see what's going on, a lot of the time, the detail is obscured. It's mostly to show off and be like, yeah, we made these, they're cool, but they're not that practical. Heat maps are really good. So doing research with it, what have we done? What can we do? Interpolators do perform differently based on how wide a gap you want to try and interpolate all at once as compared to proportion missing. You can do a pretty high proportion missing if you keep the gaps very small, because the autocovariance structure will carry through short gaps. The longer the gap, the more a lot of these algorithms struggle. The pattern of the gaps, that's where you get into that whole field of research. Missing at random or completely at random and all these things. If you impose structure to your gaps, you can make some very emergent behavior come up. Specific features of the data you would like to be looking at. What kind of data are you interested in? What are its characteristics? Can you quantify those in a way that you can actually give a sample time series that is suitable for testing interpolators, which you can then generalize back to that class of data? The number of sinusoids and the signal to noise ratio. And then current projects ongoing, and this is where I said all those students, right? So neural network-based interpolators. They finally reached the point in the last, I give it about 2.5 years, where neural networks for time series are finally starting to actually work well enough that forecasting with them is starting to make sense. Maybe 5 years. So I have a grad student right now who's writing his master's on that very question. He's developing interpolators based on graph neural networks and CNNs to see whether he can build an interpolator that works on the kind of data I'm interested in better than my method. It's been 11 years and we still have not beat that method. We've been trying and I have not succeeded yet. I'm very hopeful Evan will actually push us over the edge. And I had a student who graduated a couple years ago who was looking on part of the hybrid Wiener. It has one step in there where it generates a pilot. He tackled that problem specifically, and it improved that by 5%. And the extension of the periodic structure to modulated periodic structure. So that's, again, generalizing what's happening and going out a little bit further. And that's Ben Ott and sorry, Yatarth did a little bit of that as well. So that's all I have to say. Thank you very much for your time. We do have a little bit of time at lunch. I'd love to chat. If you're interested in using this, it is a very nice platform for testing these things. If you're interested in this problem, I think it's very powerful and useful. We haven't gotten a lot of traction yet, but it's been 3 years of a pandemic, so no one knew it existed. So now, we're trying to advertise it a bit.
So as chairman, to kick off the question, I have a quick question just on users. I mean, can you keep track of the users?
To my knowledge, no one outside my research group and my colleague at Queen's has used this yet. I'd love it if people would, but again, it's sort of an advertising thing. I gave a plenary in Spain, and it was online because it was 2020 on this topic, and tried to tell people about it. We wrote a little paper in the proceedings of that conference to advertise it. But it's one of these things where, like, there's not that many people, it turns out, that actually do time series interpolation.
Yeah, right.
There's a lot of people who use sort of off the shelf, like really old school methods, but not many people are actually pushing the state of the art forward. And I think I just haven't found all of them yet.
Yeah, I mean, I know in the environmental science community, this would be really useful for people. So I think, we talk about sort of featuring data sets and so you do types. I think this is a great example of.
And that's why I was really excited about this next talk. So the next talk is Scotland. Isn't there coming from Scotland? But from the UK, the next speaker, interested in the exact problem of interpolating water time series. And so, I'd love to see what they're up to, and then maybe we can collaborate later.
So my question before is, a lot of the ecologists would approach this problem filling in the gap with a measurement model or process or some uncertainty. So I mean, in my own work, I've got the passives tracking even two, which is microturn efficiencies, was all across the Atlantic and Pacific. And we have satellites tracking sensors on them and tracking the satellite. And so the only way really there was you had some idea of sampling rate of your emissions. You had to build, you were forced to build some behavioral model about how to move during the time period that happened this, right? So in a lot of settings, what becomes interpolation and what is more modeling?
Domain knowledge always dominates. If you have domain knowledge and you can actually model the characteristics of living things, that's always going to be better than autocovariance estimates of the same thing, or at least should be integrated into the same. I am mostly concerned with observations of static nature. So things like geophysical fields, stuff where we're getting evolution that's very, humans are not really influencing it in a huge way. It's very, very big systems. When you start dealing with ecology, you get a lot of non-stationary emergent behavior. And that starts to be outside the realm of what I've tested. Not to say it wouldn't work. I've had people try it on all kinds of random stuff, just like I sent it to them when they tried it, but I can't guarantee anything because I don't work in those areas.
Yeah, I am interested. It sounds quite good work that your students and you are doing. It's quite impressive.
Thank you.
But the thing that I would be melting on, I have this time series and am interested in analyzing it. And I have some missing gaps. What shall I do? Because all these things that you are presenting, generating time series, but not the particular data set that I have that I would like to do the interpolation for it. And the use of the correlation and covariance, if you take an AR1 process, for example, then you include in the interpolation the correlation as a function. You see, given a model, if you are doing prediction in the future, then what you are using is the previous values and the previous correlation. But if you are doing interpolation, then you are using the surrounding values. There is correlation connected with the next observation, and there is correlation connected with the previous information. And the modeling-based approach will allow you to do this kind of thing. So I thought that I have difficulty computing, for example, the correlation function in general because of the gaps of the thing. But if you combine this with the approach of using variogram, you can actually do the calculation because you're grouping your data and generating something like that. So I just wonder about the bridge.
So I developed that interpolator specifically for two classes of series that I wanted to analyze that had gaps that were interfering with that. One was a set of space physics data from the Voyager 2 satellite as it did a close approach to Jupiter to do a slingshot back in 77 to 78. And I successfully was able to reconstruct those missing gaps to the point that the estimators were giving me numbers that made sense. I was getting estimates out and I was able to observations. That was my master's thesis. I then did that for a whack load of environmental data, temperature, although less so because those tend to be pretty good, but air pollution in particular. Air pollution monitors have lots of missing data. And reconstructing those and then amalgamating them into these block census division level has been very successful. And we've been doing that for Health Canada for now 12 years. So we are applying it directly to real time series and it's working. The framework I had Sophie build as part of her research was to give you confidence in the performance of the interpolator. So what you want to do is have some source time series that act like the ones you know you want to analyze, but are complete. And then test it on all the variations of all the different ways the gaps could be there. And if it performs well, then you have some confidence that if you take that same method and apply it to a one and done n equals 1 statistical case of the series you actually care about, it will probably work. And that's what it was for, was this, it's all well and good to be like, I have an interpolator, apply it to your time series. And, I've seen people do these empirical orthogonal function things and think that they can interpolate 800 years of missing paleoclimate data. And I'm like, you just put a smooth function through 800 years. Like, what is this? Do you think that's how the link core, and they blindly do it. And this is supposed to be a way of saying, look, you can at least test the performance of this thing you think is amazing. If it does a great job on the kinds of series you are interested in, then have some confidence. But otherwise, you're right. Like here's a time series, here's some gaps. You get one shot. You don't have an ensemble. You don't have replicates. You have one time series. And that's the wonderful and terrifying thing about working in this field is you get one series. And the longer it runs, the more powerful and useful it is. But you just have the one. And knowing how to put it back together is genuinely hard. Now, I have just talked for 10 minutes of not my time, so I'm very sorry, Nura. We do actually have time, though. We're okay. We're 12:30, so I'm going to pass over to you. Just there. Right.
Do I just click on it? There it goes. Okay.
Okay. Good morning, good afternoon, depending on where you are right now. I am Noura Umar, a PhD candidate at the University of Strathclyde, and I am presenting on a joint work with my primary supervisor here at University of Strathclyde, Alison Gray. We are looking at, rather than, it's an application, not maybe like developing a package, so to say, like what Wesley just highlighted. But however, here we are trying to look at maybe which of these imputation method works on this univariate data that we are dealing with, because majority of imputation method works on inter-attribute correlations. They are basically built on that pattern rather than time dependencies. So basically that is what we are looking at to see how this method works. So without, I think you can all see my screen.
We can, yes.
Yeah, thank you. All right. So basically, Wesley have just said everything about what missing data is or what is missing values or data gap. So data gap is mostly a persistent problem now we have to deal with before carrying out any analysis. And what is this? How do we handle these missing values? There are various approaches to handle missing values, but the most famous among those is missing value imputation, which is classified into two. We have the single imputation and multiple imputation. Single imputation is a situation whereby we are replacing each missing value with a single value. Or however, when you have two or more values to replace each missing value, then we have what we call multiple imputation. So basically this work is on water level data set, which is a univariate data. And so we are only interested in single imputation method in this situation. And as I said earlier, basically majority of the single imputation method that we have in the literature are not related to time dependencies, but however, they are just correlated related attributes. So we just try to look at, okay, what will happen if we have time dependency in the data? How does this method works? Or maybe if we have method that handles time dependencies, how does it perform on this kind of data set? So it's just like a comparative studies. It's a comparative studies anyway. So we just look at how does this method performs on the real data set. So we are looking at three methods. We have the seasonal decomposition method, the Kalman smoothing method, and random method. So we are looking at how this method, how these three methods performs on this univariate water level that we are looking at. These methods are the seasonal decomposition, for instance, is it incorporates the time dependencies. So we assume that based on what the author of this package said, or of this method said, is that it will incorporate the seasonal decomposition. So it will incorporate the seasonality of the time dependent of the time series data into it, and it will predict the missing values accurately than the random method or the Kalman smoothing method. So all these methods are available in the package, input TS package by the Moritz and Bart Belstein. Okay, so we consider two approaches. The first approach is like, we just considered we have actual values, then we have this missing, we create missing values, then we now impute these missing values using these three methods. Then we now compare the actual and the imputed values first. Then the second approach is we have this, we compare the imputed values and compare it with ARIMA models. We compare it with the values fitted from auto.arima function in R also, so to see how does the fitted values relate with the imputed values. So it's kind of like two situations to see, is it the same approach? We use the same method, the same three imputation method in each approach to see how does this work. So the data we are interested in is Kainji, is from Kainji Water Station in Nigeria, and is on the map you can see the position in Nigeria is along the river Niger. And we have the time plots for this data set. So we are having the data set from 2010 to 2017, and it's a monthly data set. And the reason why we are interested in this is because we have this data is complete, but however, we have some other stations that are having missing values. So we feel like, okay, so we have these missing values and we want to analyze this data. How can we go about it? So we feel like it is important if we can look at ways to input those missing values in the other water stations and to see how it will work and come up with appropriate method probably that we can say maybe we can use to input those missing values and maybe use in our analysis henceforth. The next thing we do is these are the processes we followed because the data are on hourly basis, but some of them are missing still. So we try to convert the hourly data to monthly data. And from the complete data set, we now generate missingness using 3 different mechanisms at 5%, 10%, 20, 30, 40, and 50%. We use these 3 mechanisms, the MCAR, missing completed at random, MAR, missing at random, and missing not at random. And we now use 2 performance accuracy measures as stated earlier, some of which have been highlighted earlier, like the RMSE and the MAPE, to assess how the method performs on this data set. So the first approach we looked at is comparing the actual and the imputed values. So, and the 3 accuracy measures are being, we can all see the 3 accuracy measures, the MCAR, the MAR, the MNAR. So we look at 5, 10, 20% for now. And this is just for the RMSE values. And based on this, we can see that the seasonal decomposition is having lower value of the RMSE and across all 3 different mechanisms, missing value mechanisms. And the random method happens to perform woefully than the other 2 methods, and Kalman smoothing is not doing badly. And we have the box plot to see how this method works. And the most interesting thing here is at 5% under MCAR or all the 3 mechanisms, we can see that the random forests have a wide spread at this level, but as we go on, it keeps on reducing. So the random method is doing badly at lower percentage, still is doing badly at even like 10%, 20%. But however, the margin for the spread of the values that it predicts is coming closer. So which is a good thing, but it's still way, way bad. It performs way badly than the rest. And the next approach is instead of us considering maybe, let's say, the 20, the 30, 40, and 50% under the first approach, because we realized we are having kind of the same result. We just felt like, okay, let's consider the second approach. And because of time, had it been, I know we will have like much time, I will have just added the other one, but I feel the result is the same. So let's just look at the second approach on the second half of the missing values. We considered, the percentage missing values we considered, which is 30, 40, and 50. But this is under the second approach. And where we compare the imputed values and the fitted values from the ARIMA models. The ARIMA models are being simulated from the auto.arima function in R. So it's like we just try to compare those values from the imputed values and the fitted value, rather than in the first instances we compare the actual values and the imputed values. So here we are looking at the values from the fitted models and the imputed values. And also here we can see that still the seasonal decomposition is doing well, and the KS, which is the Kalman smoothing, is doing good as well, but random method is still way, way bad, because it's one of the random method is one of the simpler method, which is it's not even it's not having these time dependencies in it. So it's not surprising the way it is performing on this data set. And these are the box plot for the second approach, which we can still see the random method way up and is doing badly, so to say. And we can see that from this so far, so we just considered two approaches. The first one we considered the first percent, we considered 5 to 10% here, and but in the initial work we considered 5 to 50%. Then the second approach also we consider that, but because of time, we just look at 5 to 20 in the first instance, and the second instance we look at 30 to 50. So, but the result is consistent across the two approaches. And based on that, we now come to the conclusion that we also look at the MAPE as well, but we didn't put the result here. And also coincidentally, the result seems to be consistent with RMSE values. So they are kind of consistent, saying that, okay, having these time dependencies in predicting the time series values for the univariate time series is very important. And it's kind of like it captures the imaginative of the data set. It's kind of like training, it's mimicking the data set well than the other two methods that we considered. And under the three mechanisms we considered, the missing values mechanism, the MCAR, the MAR, and the MNAR. So all these missing values mechanisms produce kind of similar results on the method we considered. So what we just did is like, we just compared this method using these three mechanisms, and the result seems to be consistent irrespective of the missing values mechanisms we consider. The Kalman-Smoothing method happens to be the second best method. The seasonal decomposition happens to be the best method, while the random method is the worst among these three methods we considered. And because of this, we felt like having this seasonal decomposition method is important in imputing missing values, because missing values is something that we cannot run away from. It's here to stay, because there are a lot of reasons why we have these missing values, as stated by even Wesley in his talk. So there is no way we can leave this. We can go away with these missing values. So it's something that it's here to stay. So we have to look for ways to how to deal with that, especially in univariate water levels data set, which is kind of like people don't usually use it. And coincidentally, I'm happy to see this this package by Wesley, and I have not even come across it for once during my, maybe because of the COVID and stuff like that, but I will try to see what can be possible in doing that. And the data set we use is using is from the Nigeria Hydrological Services Agency, which is where we collect the data set from, and the data set are cut across various water stations, and these water stations are on the rivers, and we have two major rivers in Nigeria. We have the River Niger, we have the River Benue. So these water stations are basically on these rivers, and our study here is just to look how we can try to impute these missing values. And now we are done with the study on missing values. What we are looking at next is we are trying to fit some machine learning method on how to predict not the missing values anyway, how to predict the water levels now. We are now into predicting the water levels rather than replacing the missing values. So basically that is just on what we have today, and these are some of my references. Thank you for listening.
Well, thanks very much, Nura, for that interesting talk. And actually, I've been recently, I was involved with some colleagues in Benin, and we were doing some work with Streamflow. They had a lot of different stations there. They have quite a network of data. And one thing that we explored was with Earth observational data. There's a source of data called GeoGlows, which I can maybe email you afterwards, that you might want to incorporate. I mean, it's sort of present day, and they actually do some forecasts from it. So, I mean, it's not going to replace the historical picture, but it might be an extra source of data that you could link into some of your modeling work. In fact, I think some of that Earth observational derived data requires some interpolation. So, it's another activity for you to maybe consider. Yeah, I guess, are there any other questions? We have some time, right?
I mean, I don't have questions so much as just, well done, you're tackling the problem, that's the hardest thing. And getting the data ready for forecasting. I mean, forecasting is where the power comes, so that's good work. If you would like to do any retrospective analyses, I'd be happy to work with you to try other methods, use the framework, makes it really pretty graphs that you can then embed in your papers or your thesis on, how you validated your interpolation before you had trusted it for forecasting.
You'd be Wesley's first user in Nigeria to apply this method.
Yeah, thank you, Wesley. That's a wonderful. I think from the onset, I just felt like, okay, this is this is one of the environment that somebody can try to make some networking and probably improve your own research that you are currently doing or any other thing that you intend to do later on. And I think it's interesting the way it has gone so far.
It's really interesting that you were mentioning the neural network interpolator.
Yeah,
It's
we've got it down to only 5% worse than the method I pulled out of my butt in 2010. Which I made up.
I think that's the chief.
And it worked, and I've been trying to beat that performance for over a decade.
Okay.
And haven't been able to.
So maybe some machine learning might. Might help.
So, yeah.
Okay. Great. Well, thanks everyone, and I guess lunch is on the way.
Lunch is on the way. Thank you, everyone. We have a different Zoom room this afternoon, so please rejoin after lunch at the other link.